characteristics of a subspace.
Zero vectors, V is in H.
Yep. Contains a zero vector. Yep. 2. Closed under addition.
What does that mean exactly?
That means that if you add any two elements in the space, think of it as a set. If you add any two elements in the set, the result is also in the set.
Okay.
So if you think about it in terms of the integers, anytime you add two integers, 7 and 10, you get 17. 17 is also an integer, so we say that the integers are closed under addition.
Oh.
When you add any two, you can't get outside of the set.
Is there a way to express that in set builder?
No, but well, if you wanted to express it symbolically, you would say, like, for every u and v, right, you would say u plus v, right, is always an element of whatever you named your vector space, like capital V maybe. Yeah. And then the third one, closed under scalar multiplication. Same thing, that you never leave the space. Like if you multiply by any scalar, the result is still in the space. Right. Yeah. If V is 3 space, if you pick any vector in 3 space and multiply it by any scalar you want, you get another vector in 3 space. No, it'd be a whole. No, you could limit it like that. If you limited it like that, then it would not be closed, right? It wouldn't satisfy the definitions of a subspace. Okay, so I handed out some notes. Let me pull those up so we can go through them together. Okay, so we're going to talk about vector spaces. 4.1 is called vector spaces and subspaces. So R2, R3, and Rn, like you were just saying, right, are specific examples of a more general thing called a vector space. Okay? So R3 is 3-dimensional space. So we call it space, and so we're trying to generalize this idea. What makes it a special kind of space? So we call a vector space any non-empty set V whose elements, which we will generically call vectors in R3 and R2, R4, the elements actually are vectors, but you'll see that we can actually expand this to things where the elements are not vectors, but we're still going to generically call them vectors. And a vector space has to satisfy all 10 of the following axioms. Okay, so these are the basic properties of a vector space.
So it's like they are all true or all false?
They have to all be true for it to be a vector space. If one of them is false, you just say it's not a vector space. As soon as one thing fails, so they're not all true or all false. They're either all true and you have a vector space, or they're not all true, which means 9 of them could be true and 1 of them fails, in which case it's not a vector space. Okay, so closed under addition, we just talked about that, right? For any 2 elements in the set, when you add them together, the resulting element has to also be in the set. We have to be commutative under addition. In any R real valued space, R2, R3, R4, that's obviously true, right? You can add 2 vectors in either order, it doesn't matter. Associative property also has to hold. Same thing in Rn, those feel natural, right? The 0 vector must be in the space, which we call the identity element under addition. There has to be something that you can add and not change anything. Okay, so for each u in the space, there has to be an opposite of u, right? So that you can add them together and get 0, the identity. So that is, V is invertible under addition. And then you have to be closed under scalar multiplication. We just talked about that. Again, that feels natural with the Rn spaces. If you pick a vector in R2, like 1, 1, multiply it by any scalar you want. If you multiply it by pi, you'd get pi pi. That's still in R2. Okay. So closed under addition and closed under multiplication. We have a distributive property under scalar multiplication. Again, also feels natural when we're dealing with Rn. With respect to. Yeah. For real scalars C and D, this is another sort of distributive property, but here we're distributing a vector to two scalars as opposed to a scalar to two vectors. So all of these things are just properties of real numbers, so they feel natural when we're in Rn. Okay. So these are all properties that we've worked with for a long, long time. And this is associative property under multiplication, which is natural for real numbers. And then we have to have an identity element for scalar multiplication, which typically is 1. There has to be something when you multiply by it, you get the thing back. All right, so from these 10 axioms, so those are the definition of a vector space. Any set that you look at, you could prove it's a vector space by going through all 10 of these items and going check, 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 check. Right? You have to check off all 10. And then from those 10, you can prove a few more facts. You don't have to show these are true to make it a vector space, but if you know it's a vector space, you know they're true. Okay. So the zero vector is unique, meaning there's only one vector that you can add to other vectors and get the original vector back. For any u, the opposite of u is unique. There's only one additive inverse. 0 times u always gives you 0. C times a zero vector always gives you the zero vector. And negative u is the same thing as negative 1 times u. All right, so it should feel pretty obvious that Rn is a vector space. These are all properties of real numbers that you've studied for a long, long time. So there are lots of other things that satisfy these same properties, right? The set of all cubic polynomials satisfies these properties. Okay, so the set of all cubic polynomials is also a vector space. The set of all real valued functions, any function f, like think of all the functions you know, right? Put them all together in one big set, it satisfies all those properties, so it's a vector space. The set of all doubly infinite vectors. So if you go all vectors, infinity to the negative and infinity to the positive, a vector space. Okay. All right, I'm going to erase this for a second. So there, like I said, the Rn's feel natural because these are all properties of real numbers, but there are lots of other things that can satisfy those properties. All right, now this one, the subspace theorem, is like a super nice one. If you already know H, if it's a subset of something you already know is a vector space, right? Like, let's think about the even numbers, right? We already said the integer. No, okay, never mind. Pretend I didn't say that example. Okay, some set H. If it's a subset of a vector space, V. So you have to know that the bigger thing is a vector space. So that is often given, or like there are some that we start to recognize because we use them a lot and we know they're vector spaces. If H is a smaller piece of that, it only has to satisfy 3 properties to know that it's also a vector space. And we call it a subspace because it's a subset and it's a vector space, subspace. Okay. So it only has to satisfy these 3 properties, that the zero vector has to be an H, and it has to be closed under addition and scalar multiplication. So just the zero vector as its own set, it's a subspace of every vector space because every vector space has to contain the zero vector. The zero would be a subset of a known vector space. It's closed under addition and closed under scalar multiplication. So it's always a subspace. The set of all polynomials is a subspace of the vector space of all real valued functions. So if you think about every function you can possibly think of that you learned in like college algebra and pre-calc, put them all in one big set, right? If you just pull out all the polynomial functions, that's a subspace, right? It satisfies those three properties, and it's a subset of a vector space. And the set of all cubic polynomials is a subspace of the vector space of all polynomials, right? From the bullet above, we know the set of all polynomials is a vector space. So pull out all the cubics. That's a subset. It contains the zero vector. It's closed under vector addition and scalar multiplication, so it's a subspace. Yes.
Are there any other, polynomials?
Yeah. All of them. Yeah. Yeah. So let's look at if we look at a subset of R3, right? We know R3 is a vector space. If I look at just this subset, all the vectors that look like A, B, 0, right? It's a subspace because is 0, 0, 0 in there? Yep, just choose A, because A and B here can be any real number. So yeah, 0, 0, 0 is in there. Closed under vector addition, if I add up any two, like A, B, 0 with, say, C, D, 0, I get A plus C, B plus D, 0, right? The same kind of vector, a real number, 0, right? So I'm closed under addition. And closed under scalar multiplication, if I take A, B, 0, and I multiply by any real number I want, like let's say 3, right? I'm going to get 3A, 3B, 0, which is still in the set because that's still a real number, 0. AB1 would not be a subset because it wouldn't contain the 0 vector. Yep. ABC would be the entire vector space R3. Yep. I think I misspoke. I'm not sure. AB1 is a subset, but it's not a subspace. AB1 is a subset of R3. It is a smaller collection of things from R3, but it's not a subspace because it doesn't satisfy the three properties. Okay, so for any set of vectors contained in a vector space, the span of those vectors is a subspace of V. So you can always make a subspace. So if you know there are two vectors in your vector space, if you take their span, you get a subspace. So this is helpful for proving if a set is a subspace. We call the span of the vectors the subspace spanned or generated by the vectors. And a set of vectors whose span generates a subspace is called a spanning or generating set. All right, let's look at a few examples. Okay, so V is the set of all vectors AB such that A and B are real numbers. A is bigger than or equal to 0, B is bigger than or equal to 0, and B is less than or equal to A. So let's try to come up with three vectors that are in V. 1, 1, 2, 2, and 3, 3. Okay, that is true. Like, someone give me another one that doesn't look like AA. 5, 4. They're both positive, and B is smaller than A. That's good. 5, 4. How about one with some negative numbers? Oh, yeah, you can't, because A and B have to be positive.
Yeah, good question.
0, 0. Yeah, that satisfies it. Yeah. Yeah, like 10, 8, right? Good. Okay, if U and V, if you pick two random vectors in this vector space and add them together, do you always get another vector that satisfies those conditions? Yeah. So if I do 1, 1 plus 2, 2, I'd get 3, 3, and that is in the set. What if I do 5, 4 plus 10, 8? 5, 4 plus 10, 8. I'm going to get 15, 12. The result, they're both positive, and my second entry is smaller than my first. Will that always happen? Yes. Yeah, because my 2 second entries are going to be smaller than my 2 first entries. So this will always happen. So yes. Okay. So that tells me that V is closed under addition. All right, let's find one specific vector V in the set and a specific scalar C from the real numbers so that when you multiply C times V, you do not land back in the vector space. Sorry, you don't land back in the set. Yeah, you could pick C -1, right? So if I do -1 times any of these vectors I picked, like 5, 4, right? My result is -5, -4, which is not in V, right? It's not in the set V because my entries are negative. So this is not an element of V. So this means that V is not closed under scalar multiplication. So let's see. I'm going to write closed under addition for B. And this tells me that this is not closed under scalar multiplication. Okay. When it's not closed under scalar multiplication, V is not a vector space. So is V a vector space? No. C part C, right? Not closed under scalar multiplication. Okay, so this is sort of the general idea that we're starting with. I'm going to give you a set, and you're trying to determine whether or not it's a vector space. So let's do another one. We kind of already know because we just talked about this in the notes, but if H is A, B, 0, A and B can be any real number. Give me 3 vectors in H. 2, 1, 0. 1, 2, 0. Good. Good. Okay. Just pick any real numbers A and B, throw them in the first 2 entries. Third entry has to be 0. Is H a subset of R3? Yes, it is definitely a smaller piece of R3. Okay. So we know it's a subset of R3. R3 we know is a vector space, right? So I only have to prove these 3 things, that 0's in there, that it's closed under addition, closed under multiplication, and I will know that H is a subspace. Is the 0 vector in H? Yes. Yep, because you can just make A and B 0, right? Because the set is defined so that A and B can be any real number.
But actually, I have a question.
Yes.
It says A and B. Do they have to be different integers?
Nope. They just have to be not necessarily the same integer, but they don't have to be different. If I wanted them to absolutely be different, I would write it. I would have to add another condition: A does not equal B. Yeah. Right. Right. Is H closed under vector addition? Let's pick a couple of our vectors. Let's pick 2, 1, 0, 2, 1, 0 plus 1, 2, 0. When I add them together, I get 3, 3, 0. Is 3, 3, 0 in the set? Yeah, it's a real number 0, which is how we define the set. So yes, this is closed under vector addition. How about scalar multiplication? Yeah, so if you pick any real number, I could pick pi, right? Multiply by -1, 2, 0. So I get -pi, 2 pi, 0. Does that satisfy the conditions of being in H? Yep, it's a real number, 0. Yes, so no matter what I pick for my scalar multiplication, I will land back in the set. So is H a subspace of the vector space R3? Yes, satisfies all 3 conditions. Okay, it's a subset of a known vector space, and it satisfies the 3 subspace conditions. All right, one more we'll do together. So I'm looking at another set H that looks like A, B, 2A plus B. So give me a couple vectors in this set. 0, 0, 0, that's good. 1, 1, 3. Yep. So you pick two random numbers for your first two entries. So maybe I could do like 2, 4 for my random entries, and then 2 times the first entry. 2 times 2 is 4, plus 4 is 8. 2, 4, 8. Okay, is H a subspace of R3? Yeah. Well, it's definitely a subset of R3, right? These are all these vectors are definitely in R3, so it's a subset. It contains a 0 vector, so it's a subset of R3, right? Check. It contains 0, check. I have to think about the closed under multiplication and addition. So closed under addition. Okay, so let's see. Let's just pick 2 and add them together. If I do 1, 1, 3 plus -1, 1, -1, I get 0, 2, 2. Is that 2? Is 2A plus B my third entry? Yeah. Will that always happen? Let's do one more. Let's do one more and try to convince ourselves. Let's do -1, 1, -1 plus 2, 4, 8. So I get 1, 5, 7. 2 times 1 is 2, plus 5 is 7. Yeah. Yeah. Okay, so we're pretty sure it's closed under addition. We've done 2 examples. We really should be a little more careful. Like I should pick more generic vectors and add them. Like I could pick an A, B, 2A plus B, and add a C, D, 2C plus D, right? So these are more generic versions of what things in this set look like. So this becomes A plus C, B plus D, 2A plus 2A plus 2C plus B plus D, which I could simplify that third entry to be 2 times A plus C plus B plus D. Right? Yeah. So it will always work no matter what two I pick. Yeah, now let's think about multiplication. So multiplication. So somebody pick a C, 5. If I multiply 5 times 1, 1, 3, I get 5, 5, 15. That's 2A plus B does give me the third entry, 15. Will that always work? No? Yes? I think it always works. Let's do a generic version, just like we did over here, just to double check. If I do a generic C times A, B, 2A plus B, I get CA, CB, C times 2A plus B, right? But then distribute that C in the third term there. So I have CA, CB. I have 2 times CA. That's C times, I'm distributing my C, plus CB, which is twice the first term plus the second term. So this one will always work also. Okay, so same kind of ideas in your group activities. I'm giving you sets. You tell me whether or not they are vector spaces or subspaces, or neither.